Hello everyone, myself Rajvee Shah from MSc Statistics Semester 2, Department of Statistics, Sardar Patel University. Today my seminar topic titled Multicollinearity. Whenever we try to learn something new, we always wanted to know about that, right? So let's see its introduction. If there is no linear relationship between the regressions, they are said to be orthogonal. What is regressors? So regressors is an independent variable in our regression model. So if there is no any linear relationship between the independent variables, we can say that they are orthogonal. Unfortunately, in most applications of regressions, the regressions are not orthogonal. That means there is some linear relationship between the independent variables. Sometimes the lack of orthogonality is not serious. However, in some situations, the regressors are nearly perfectly linearly related, and in such cases, the inference based on the regression model can be misleading or erroneous. Lack of orthogonality is not always serious, but in some situations, like in cases of inference-based regression model, there is a perfectly linearly related regressors are present, so it gives a misleading result. When there are linear dependency among the regressors, the problem of multicollinearity is said to exist. Let's see its definition. Multicollinearity is a statistical phenomenon and is said to be present when an independent variable is a linear combination of some or all of other independent variables in the model. So basically, multicollinearity is a statistical phenomenon. Is said to be present when an independent variable is a linear combination of some or all of the other independent variables in the model. Here, we consider x1 and x2 two independent variables. When uh, two independent variables are linearly related, we say there is a collinearity. But when one independent variable are linearly related to more than two independent variables, we say that that is a vertical linearity. So in this image, you can see that here x1 between x1 and x2, there is no any linear relationship between them, right? So there is no collinearity. Here, this is some portion are mixed with each other, so there is a low collinearity. Here, portion is bigger than this figure two. Right, so it is a moderate collinearity. It is a high collinearity, and this is a very high collinearity. So we know about the take introduction. We know about its definition. So when it comes about, so let's see its sources. There are four primary sources of multicollinearity. One, data collection method employed. Second, constraint on the model or in the population. Third, model specification. Fourth, an over-defined model. So first is the data collection method employed. Sampling over a limited range of values taken by regressions in the population. So here are we talking about a limited range of values. So what is a limited range? Suppose for the independent variables, you take value 1 to 5, and on the other hand, you take value 0.1 to 0.5. So 0.1 and 0.5 is a very limited range, and 1 to 5 there is a scope of values for the independent variables to taken, right? So sampling over a limited range of values taken by regressions in the population. So if this situation is happening, so that is we can say that multiple linearities may present. Second is constraints on the model or in the population. constraints on the model or the population being sampled. For example, in the regression model of electricity consumption Y on income X2 and size of house X3, there is physical constraint in the population. The family having higher income generally have larger house than the families with lower income. It is very clear that if some person's income is a high, he or she bought a bigger house, right? So if there is a number of rooms are more, so electricity consumption is also high, right? So the family having higher income generally have larger house than the families with lower income. Right, if there is any this kind of physical constraints are present in the population, we can say that there is a multiple inheritance. Third is model specification. So model specification, for example, adding polynomial term to regression term is especially when the range of x variable is small. So adding a polynomial term means generally our regression model is y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon, right? So there is only x1 or x2 term, but instead of x1 x2 we can say that x1 square. So that is a polynomial term. Model specification is if we add a polynomial term to a regression term in a range of where the range of x is so very small. If there is a range of x variable is a small and you add a polynomial term, so this model specification may leads to multiple linearity. Right? And fourth is a over-defined model. Fourth is over-defined model. That means if somewhere there is unwanted variables are present in our model. So we can say that it is an overdefined model. Let's see about it. This happens when the model has more explanatory variable than the number of observations. This would happen in medical research when there may be small number of patients about whom information is collected on a large number of variables. That means in a medical research, there is a very limited number of patients, but information is a very large. That means variables are very large number of amount, but observation is very small. So it is an over-defined model. So whenever it's over-defined model, it will leads to multiple linearity. So type of multiple linearity where there is a different kinds of multiple linearity. So here we consider two types of multiple linearity. It's one is an exact multiple linearity, or we can say that it is a perfect multiple linearity, and second is a near or less perfect multiple linearity. So first of all, we say we let's see about exact multiple linearity. If two or more explanatory variables have an exact linear relationship between them, then exact or perfect multiple linearity is said to be present. For k variable, regression model having x1, x2 or so on up to xk regressors, where x1 is equal to 1 to allow for intercept term, an exact linear relationship is said to exist if the following condition is satisfied. A1 x1 plus A2 x2 plus 1 up to AK xk. So if this condition is satisfied, we can say that there is a exact multiple linearity. Suppose we consider modeling the monthly electricity bill as a function of household income x1 and the household expenditure x2. If x2 is equal to x1 minus savings and the saving value is constant, there is an exact linear relationship between x1 and x2. This is a near multicollinearity, or we can say that it is a less perfect multicollinearity. When linear relationships among explanatory variables are approximate, then near multicollinearity is said to be present in the model. This can be represented as a1x1 plus a2x2 plus a2 plus mu 1. Now you can compare this to types of multicollinearity. Here in exact multicollinearity, there is no any new item or any error term, right? So in exact multicollinearity, you can say that there is no scope of any error. It is a perfectly correlated to each other. There is an exact relationship between two independent variables. But on the other hand, in near multicollinearity, there is this new item where is a stochastic error term. In some books, disturbance or noise word are also used for this. And here, this is a new one is a stochastic error term. That means what is means stochastic means randomness are present in error. The example, the consumption function model suffers from near multicollinearity, where current income in wealth measure similar attributes to individuals' ability to undertake consumption expenditure. Right. So individuals' ability are attributes which are affecting the wealth measures. So there is a near multicollinearity is present. Uh, some assumptions are there. So violation of that assumption leads to multicollinearity. So let's see about that. Multicollinearity, violation and the assumption of the classical regression model. One of the assumptions of classical linear regression model is that A. There is no exact linear relationship between two or more independent variables, and second is the number of observations is at least as many as the number of independent variables. Before in the sources, we talk about this, right? So there is no exact linear relationship between two or more independent variables. So as per before we see, so that is orthogonality is must. If orthogonality is one, then so we can say that it may leads to multicollinearity. If the number of observation is at least as many as the number of independent variables, number of observations is at least as equal to the independent variables. If this assumption also violated, so it may leads to multicollinearity. The presence of multicollinearity leads to violation of this assumption and has consequences related to uniqueness, statistical significance, and precision of the OLS estimators. The presence of perfect multicollinearity makes it impossible to compute the OLS estimates of the regression model. So, if multicollinearity are present, so its consequences related to uniqueness, statistical significance, or precision of OLS estimator. Right? So if perfect multicollinearity is present, so it makes impossible to compute OLS estimator of the regression model. Right? So we see its introduction, its definition, type of multicollinearity, what are the assumptions which are violated. So we can say that there is a multicollinearity present. We know about the sources. So all of these things are known. We already know about that, right? So now let's see its effects. So the presence of multicollinearity has number of potentially serious effects on the least square estimates of the regression coefficients. Some of these effects may be easily demonstrated. Suppose that there are only two regression variables x1 and x2, the model assuming that x1, x2 and y are scaled to unit length Here you can see beta not term is not present here, right? So if unit length means we take its normal form, we normalizing it. So beta not term, we can say that beta not term is disappeared from here, right? So the presence of multicollinearity has a number of potentially serious effects. If there is a multicollinearity, there is a potentially serious effect in least square estimates and regression models, right? So here models we have this is our model we considered here, and the least square normal equations are x dash x beta cap is equal to x dash y. This is our correlation matrix, and our diagonal elements are 1, and this is R12 and R12. This is our correlation matrix of diagonal elements are correlate. Beta 1 cap, beta 2 cap, R1y, R2y, where R12 is a simple correlation between x1 and x2. And RIY is the simple correlation between xj and y, where j is equal to now the inverse of x dash x is. We know that inverse of matrix, right? So we divide diagonal elements by its determinant, and all diagonal elements are we replace the diagonal elements with each other and take minus sign to of diagonal elements. We give this one. This equation is we can say as one, and the estimation of regression are. This is the value of beta 1 cap and this is the value of beta 2 cap. It is come from this matrix multiplication. If there is a strong multicollinearity between x1 and x2, the correlation coefficient R12 will be large and approaches 1 in absolute value. So absolute R12 tends to 1 as R12 tends to 1. The variance and covariance of the least square estimator increases greatly. That is, variance of beta j cap c j j sigma square tends to infinity. So how this infinity comes here, right? So let's see its C matrix. So here we say here that R12 tends to 1. It tends to 1, right? So just consider here 1 minus, consider here 1 minus 1, R12 square, it tends to 1. Suppose it is a 1. So our denominator value is 0, right? That's why it's going to infinity. And covariance beta j cap, beta k cap is equal to c jk sigma square is also going to plus or minus infinity. Therefore, strong multicollinearity leads to very large variance and covariance of regression coefficients. So, different sample at the same x level may give very different estimate of the model parameter. Strong multicollinearity leads to very large variance and covariance in regression coefficient. Whenever we talk about the best model, we always consider a minimum variance. If multicollinearity are present, a strong multicollinearity leads to very large variance. So this is also an effect of multicollinearity here, right? So different sample at the same x level may give very different estimate of the model parameters. When there are more than two regression variables, multicollinearity produces similar effects. So if there is more than two variables, multicollinearity produces the similar effects, right? It can be shown that the diagonal elements of C is equal to x dash x inverse matrix R Cjj is equal to 1 upon 1 minus Rj square. J is equal to 1 to so on up to P. Rj square is basically coefficient of multiple determination obtained from regression of Xj on the remaining P minus 1 P-1 regression variable.
If there is strong multicollinearity between xj and some of the other regressors, the value of rj square will be close to 1. Since variance beta j cap is equal to cjj sigma square is equal to sigma square upon 1 minus rj square, the value of rj square close to 1 make the variance of beta j cap very large, and covariance between beta j cap and beta k cap will also be large if xj and xk are involved in a multicollinear relationship. Multicollinearity tends to produce least square estimates beta cap that are too large in absolute value. To see this, consider the square distance from beta cap to the true parameter vector. For example, n1 square beta cap minus beta dash into beta cap minus beta. That is equation number 4. Here Rj square value is close to 1, that makes Cjj sigma square means variance beta j cap very worse. And in our regression model, we always wants a low variance model as a best fit model, right? So multicollinearity is not the only cause of large variance and covariance of regression coefficients. The expected square distance expectation L1 square is expectation L1 square is equal to expectation beta cap minus beta dash into beta cap minus beta is equal to summation j is equal to running from 1 to p expectation of beta j cap minus beta j square is equal to summation j is equal to 1 to running from 1 to p variance of beta j cap is equal to sigma square trace x inverse. We give equation number 5.
Where the trace of a matrix is just the sum of the main diagonal elements. When there is multicollinearity present, sum of the eigenvalues of x plus x will be small. Since the trace of matrix is also equal to the sum of its eigenvalue, equation 5 becomes expectation Li square sigma square 1 upon lambda j, where j is equal to 1 to p. J is running from 1 to p. We give its equation number 6, where lambda j greater than 0, where j is equal to 1 to so on up to p are the eigenvalues of x plus x. Thus, if the x plus x matrix is conditioned because of multicollinearity, at least one of the lambda j will be small, and equation 6 implies that the distance from the least square estimate beta cap to true parameter beta may be large. Equivalently, we can show that expectation L1 square is equal to expectation beta cap minus beta dash into beta cap minus beta. We basically just multiplication of two brackets. So here it is beta cap into beta minus 2 beta dash cap minus 2 beta dash cap into beta plus beta dash cap beta, or expectation of beta cap is equal to beta dash cap beta plus sigma square trace of x dash x. Now, in this form is write as a sigma square trace x trace x inverse. That is, the vector beta cap is generally longer than the vector beta. This implies that the method of least square produces estimated regression coefficients that are too large in absolute value. When strong multicollinearity is present, the least squares method may give poor estimator of the individual regression coefficients. But this does not necessarily mean that the fitted model gives poor predictions. That means a strong particularity is present in least square method. It may give poor estimator of the individual regression coefficient, but it's not necessary that it also give a fitted model to poor predictions, right? It is just for individual regression coefficients. It's not about the model. If predictions are made in the region of the X space where multicollinearity approximately holds, the regression can still give satisfactory predictions because the linear combination summation j running from 1 to p beta j xij may be estimated well even if the individual parameters beta j are poorly estimated. Here in these lines, you can see explanation uh, about these two lines, right? Beta J cap is a poorly estimated, but this linear combination is estimated well. So we already show about its sources or its effect. So how can we detect multiple linearity, right? If we want to know about that multiple linearity, so there are very several way to detection. So let's see one by one. A natural question is how we can tell whether collinearity exists, especially in models with more than two explanatory variables. Multicollinearity is a matter of degree and is a sample problem. So we can't formally test it or measure it with a single method. Instead, we depend on some general rule of thumb to identify. So our first method is high R square but few significant p ratios. If R square is high, say in excess of 0.8, the F-test in most cases will reject the hypothesis that the partial slope coefficients are simultaneously equal to 0. R square, we can say that it's a coefficient of determination, right? If it exceeds from 0.8, the F-test in most cases will reject the hypothesis that the partial slope of coefficients is simultaneously equal to 0. However, individual t-test may show that none of very few of the partial slope coefficients are statistically different from the 0. High R square but few significant t-ratios, that means R squared is high, but there is a few significant two ratios at present, so we can say that there is multiple linearity. Then second is a high pairwise correlation among regressors. If the simple correlation coefficient between two regressors is high, say in excess of 0.8, multiple linearity may be a serious problem. The limitation of the criteria is that although high simple correlations may suggest collinearity, they are not necessary for its existence. That is, high correlation are sufficient but not a necessary condition for the multicollinearity because multicollinearity may exist even when simple correlation are comparatively low. So always a high relations are causes multicollinearity. It's not always necessary. Sometimes multicollinearity may exist even when simple correlations are comparatively low. Examination of partial correlations. Farrar and Luber suggested examining partial correlation coefficients. Thus, in the regression of y on x2, x3, and x4, a finding that r square 1.1 0.234 is very high, but in the partial correlations, R12 and 12.34 and R13.24 and R14.23 are comparatively low, may suggest that variables x2, x3, and x4 are highly intercorrelated and that at least one of these variables is superfluous. So examine the partial correlations. So R square is R very high, right? But these are the R12.234, 13.24. These are the are partial correlations, right? So it is a comparatively low, may suggest that the variables x2, x3, x4 are highly intercorrelated and at least one of these variables is superfluous. Auxiliary regressions. Since multicollinearity arises because one or more regressions are exact or approximate linear combination of other regressions, one way to detect it is to regress each xj on the remaining x variable and compute the corresponding RG square. Each such regression is called auxiliary regressions. That means if uh, sorry, if one way to detect it is the regress each exchange on the remaining x variables. Suppose uh, we have 10 variables. So x one variable is regressed on remaining x variables. That one variable, if there is a 10 independent variables, so one variable regress to remaining 9 variable to and compute the RG square. Such regression is called a auxiliary regression. If the computed F statistic exceeds the critical F value at the chosen level of significance, the particular regression XG is co-linear with the other derivatives. Suppose a second variable a second variable's F statistics value is exceeds to critical value, so we can say that x2 is collinear with other regressions. Find its eigenvalues or condition index. Let the condition number of key be defined as k is equal to maximum eigenvalue upon minimum eigenvalue. The condition index is defined as ci is equal to under root k. Under root k means k is equal to maximum eigenvalue, minimum eigenvalue. As a rule of thumb, if K lies between 100 to 1000, there is moderate to strong multicollinearity. If it is exceed to 1000, there is severe multicollinearity. Alternatively, if the condition index is between 10 to 30, there is moderate to strong multicollinearity, and if it is extreme to 30, there is a severe multicollinearity present. Variance inflation factor (VIF), the most used method of detection of multicollinearity. The diagonal elements of C is equal to x plus x inverse are useful in detecting multicollinearity. The jth diagonal element Cjj is equal to 1 minus Rj square inverse, where Rj square is obtained by regressing xj on the remaining minus 1 regressions. If xj is linearly orthogonal to others, Rj square is small and Cjj is nearly 1. If it is nearly linearly dependent, Rj square is tends to 1 and Cjj becomes large. Since variance beta j cap is equal to Cjj sigma square, where Cjj represents the inflation in variance due to multicollinearity This is called variance inflation factor. VIFJ is equal to CJJ is equal to 1 minus RJ square inverse. VIF measures the combined effect of dependence among regressions. Large VIFs indicate multicollinearity. Typically, VIF greater than 5 or 10 suggests poor estimation. The confidence interval length of beta j is Lj is equal to 2 sigma Cjj square 1 half T alpha by 2 n minus p minus 1. This is a tabulated value of T. And compared to an orthogonal design, Lj upon Lj star is equal to Cjj half is equal to 1 under root VIFJ. Thus, VIFJ shows how much the interval is inflated due to multicollinearity. Now we learn about the different methods of detection. So now how can we can deal with the multicollinear? So let's see its correction measures or remedial measures. Ignore. First is ignore. E. If an analyst is less interested in interpreting individual coefficients and wants to forecast the value of dependent variable, then the problem of multicollinearity may be ignored. B. It is also worthwhile to ignore the problem if the regression coefficients are significant and have meaningful signs relatives. And C. Multicollinearity may be ignored if R2 from relation exceed any of the R and 2. That means in some cases we are not interested to interpreting the individual coefficient effect, right, or wants to forecast the value of dependent variable. So we can at that time we can ignore the problem of multicollinearity. Second is a drop variable. In this method, if one variable are showing the high multicollinearity, because of that variable, we can see the multicollinearity are present in the model, so we can drop that variable. So multicollinearity may be eliminated by dropping one of the collinearly related variable from the model, but it should be kept in mind that this involves some risk of under-specifying the model if the variable truly belongs to the model. In some cases, some variables are very important for the model. It's very significant for the model, and that variable are also cause the collinearity. In that case, if you are drop that variable, it causes under-specifying model. So it just kept in mind that this involves some risk of under-specifying models. Number third, obtain extraneous data. You can take some extra data, right? So information from the other sources about the variables or values of some regression coefficient from some related studies may be incorporated in the model. 4. Increase sample size since multicollinearity is essentially a sample phenomenon. Using additional data can often solve the problem. Before in the paragraph of correction measures, please show that multicollinearity is a sample problem, is a sample phenomena. Multicollinearity are problem of sample, not the population. So if we increase our sample size, it may solve the problem of multicollinearity. Number 5, transform the variables. The variables may be transformed. If the data is a time series data, then one may reformulate the model in terms of the first difference forms. So instead of ruining the regression model, yt beta naught plus beta 1 x1 t plus beta 2 x2 t plus epsilon t. The regression that may be estimated is yt minus yt minus beta 1 x1 t minus x1 t minus 1 t minus 1 beta 2 x2 t minus x2 t minus 1 plus mu t. And what is mu t is a epsilon t minus epsilon t minus 1. Principal component analysis. PCA is a method by which a number of collinear variables can be transformed into a set of uncorrelated or orthogonal variables called the principal components. Principal component is a method by which number of collinear variables can be transformed into set of uncorrelated or orthogonal variables. So in this method, this is a method where collinear variables are transformed, right? So it's called a principal components. These principal components are artificial variables that are constructed in a manner such that they account for most of the variance that is caused in the observed set of correlated variables due to unobserved common factors between them. In fact, this common factor is what is called the principal component, and there are as many principal components as the number of common factors. Once the principal components have been extracted, the regression may be run on those orthogonal variables in place of the original collinear variable. Before we take the collinear variables, we can transform it and it makes a principal component. So basically, this is the artificial variables, and where we can add this artificial variables in the our regression model. So our regression may run on this orthogonal variables in place of that original collinear variables. However, one drawback of the principal component analysis is that generally it is not possible to interpret these principal components in a meaningful way. Before I said that it is artificial variables. So sometimes we can't interpret it in meaningful way. So, in order to interpret the regression coefficient in a meaningful way, the regression coefficients of principal components are transformed back into the regression coefficients of original variables after running the regression. So, this is the example. We see that example. This is a example of one book. So, this table or presents the data concerning the percentage of conversion of N-heptane acetylene and uh, three exploratory variables. These are typical chemical process data for which a full quadratic response surface in all three regressions is often considered to be appropriate tentative model. A plot of contact time versus reactor temperature is shown in figure. Since these two regressions are highly correlated, there are potential multicollinearity problem in this data. This is a full quadratic form, and this is a data, right, which we are considering. This is the R code of this data. We put her data in this data frame. We form a model, and here it is its output, right? So we can say that this is a model output, and coefficients of all uh, here with t, h, and this partial correlations are there. So it is coefficients and estimated and standard errors and t values, and this is the all p values, right? So detection of multicollinearity, here for the detection via VIF, we need to install we need to call a car library. So VIF, so this is the some interpretation. This is a common measures. So VIF is equal to 1. So there is no multicollinearity. VIF is greater than 5. So it is a moderate multicollinearity. And if our VIF is greater than 10, so it is a very serious multicollinearity. So this is our all the VIF according to our model. So in this first, for the T is an extreme high multicollinearity. For the H is also very severe. C for the severe. And its total overall is a very high multicollinearity are present. Right. So it is a remedial measure. So this is our quadratic model. So in this quadratic model, centering variables are very useful, right? So using this data, we are centering our variables, and we again defined a model, we built a model, and then after again we find a VIF, and then after we here you can see this a VIF model center, right? So these are the VIF. So here its output. You can see this, but still here is a very high multicollinearity also present here. So in this, remove highly correlated variables if needed. So in this VIF, we see that there is still it's a very high sum of variables. Some of quarter in this model, some of variables are still it's very high VIF. So there is a multiple linearity at present. So in this data, we can here principal component regression. So in remedial measures, we see that principal component analysis is also one of the correction measures, right? So we for that we need install a package PLS, and then we call it. So again we form a model, and in this here what we say, remove highly correlated variables. So in this output, you can see this TC, this CC, this I, and this I also. So HC, I, and this both are it's have very low VIF. So here you can see that we form new model, ignoring that and removing that very highly correlated variables, and this is its uh, output, right? So it's a and this is its summary. So by this example, we learn about how we can detect the multicollinearity, and with the different methods how we can handle this multicollinearity. Hope you learn something new with this seminar and with this video. Thank you so much.